Hello everyone, can you hear me? Am I audible? Okay, so we will start in 1 or 2 minutes more. I will wait if anyone joins. Then we will start the session. Okay, let's start. So, my name is Rajoy Mukherjee, and I'm a research scholar at IIT Kharagpur. So, I will be conducting this live session for NPTEL course on computer organization and architecture. So we will be solving some basic problems which are related to what the questions can be asked at the exams and also for this week's assignment. So it will be interactive, so please feel free to ask any question in the chat. I will respond to all. Also the video is being recorded, so you will be able to get the video after the session. Okay, so let's start. So this is the first question. Our processor have a clock cycle of 5 nanoseconds. What will be the clock rate in megahertz? So frequency frequency is given by 1 by clock cycle. So in this case, clock cycle is given 5 nanoseconds. 5 into 10 to the power minus 9 seconds. So it will be 1 by 5 into 10 to the power 9 seconds, which is basically 0.2 into 10 to the power 9 seconds, which will be, sorry, not seconds, Uh, so it will be hertz. It will be 200 hertz, megahertz. Okay, that is you can understand. So you, this is a basic formula, basic question that like very preliminary, and it will help you in the corresponding questions in the next few slides. So you, any of you have any doubt, you can ask regarding this. So, okay, I will then go to the next question. So the question is, suppose a program requires 1000 instructions to execute. So the program has 1000 instructions. The average number of cycles per instruction, that is CPI, is 1.5. The clock frequency given is 2 gigahertz. So what is the time required to execute the program? So the given is how is the execution time calculated? So execution time xt is equals to IC into CPI into C, clock cycle. So here IC is given, that is the number of instructions. Number of instructions is 1000. CPI is given as 1.5. CPI is given is 1.5 cycles per instruction, CPI, and frequency is 2.0 gigahertz. So 2.0 gigahertz. So then what will be the clock cycle? Clock cycle will be 1 by f. It is 1 by 2 to the power 10. So execution time will be 1000 into 1.5 into 1 by 2 10 to the power 9, which we can write as 500 into 1.5 into 10 to the power minus 9. So this will be seconds, 750 nanoseconds. So this will be the answer, 750 nanoseconds. So you can ask if you have any doubt regarding this. Is this clear? Okay. You can ask if you have any doubts. CPI is cycles per instruction. Yeah, see, it is written the average number of cycles per instruction, CPI. So, so first, the execution time. So this is the general formula, like xt equals to IC into CPI into C. So IC is the number of instructions, instruction count. CPI is the cycles per instruction, and frequency is 2 gigahertz. So, like from the previous problem, we solved like how like cycles is calculated. Total number of cycles is calculated is 1 by f. So 1 by 2 to the power 9. So that's how we substitute the values in the equation, and you get the value. Okay, so I'm moving to the next problem. So it is the question is, consider a program whose instruction count is like 1500. Average CPI is 2, and the clock cycle is 1 nanosecond. Clock cycle time is 1 nanosecond. So suppose we use a new compiler on the same program for which the new instruction count is 2500. So the program is same, but we are using a new compiler. So according to that compiler, the number of instructions now will be 2500, and the CPI will be 1.5, and which is running on a faster machine with clock cycle time 0.5 nanoseconds. So what is the speed up we are gaining? So the program is same, but we are running into different compilers, and also one has a faster machine and one has a clock cycle of 1, another 0.5. So let's simplify it. So what is the first machine? So the first machine, the execution time will be xt1 will be 1500 into 2 into 1 into 10 to the power minus 9. So this is the execution time in the for the first first compiler and the first machine. Now the second one will be number of instructions given is 2500, CPI is 1.5, and it is the running on a faster machine, so it has a clock cycle of 0.5 into 10 to the power minus 9 seconds. So what is speed up? So here the speed up is achieved. What will be speed up will achieve? So here the speed up 2 to 1, speed up that 2 achieves over 1. So it will be performance of 2 divided by performance 1. So what is performance of 2? Performance of 2 will be 1 by x2, and performance of 1 will be 1 by xt1. So we can simplify it as xt1 divided by xt2, which will be so if we substitute it, what will it be? 1500 2. So let's simplify it a little bit. So 1500 into 2 to 1 divided by 2500 to 1.5.5. So if we calculate this, it will be so it is 0.30 divided by 25 into 0.75. So it will be, if we calculate it, it will be 1.6. So the answer will be 1.6. So any doubt? This will be the answer. Any doubt regarding this? Okay, good. So we'll go to the next problem. So it says a machine X executes a program with the average CPI 2.5. So consider another machine Y with the same instruction set but a better compiler that executes the same program with 10% less instruction and with CPI of 1.5 at 4 gigahertz. What should be the clock frequency so that both machines have same performance? So so that both machines have same performance. So it is said this is a machine X and this is a machine Y. So it executes a program P. CPI here is 2.5 and the C clock frequency is unknown. Performance is inverse of execution. So it is the fundamental, like performance will be the inverse of execution time. So suppose a program, think about it. So like a program on machine X takes 8 seconds and the same program on machine Y takes 10 seconds. So which do you think is a better computer, machine A or machine B? The one which takes less time or one which takes more time? Obviously the one which takes less time. So the performance is obviously the one which has the less execution time. That is the inverse. That is what you, that is the fundamental, right? The one which takes less time will be having a better performance. So the question says there is a program machine X and a machine Y. So both executes the same program P. X has CPI of 2.5 and the instruction, the clock frequency is unknown, and suppose the IC, that is the instruction count, is X. The Y executes the same program P. The CPI here is 1.5. C is 4 gigahertz and IC is, it is said the number of instruction is 10% less. So 10% less means 1 minus 10% of x, so it will be basically 0.9x. So it is said that the execution time is same, that is xt of this and this are equal. So what will be the equation? So it will be 2.5 into, suppose c into x equals to 1.5 into 4 into 0.9 x, or x is gone, c equals to, oh, 1 minute, c is will be 1 by 4 z, or c will be 1.5 into 0.25 into 0.9 divided by 2.5. So if you calculate this, it will be 1.5 into 0.25 into 0.9 divided by 2.5 divided by, so it will be 0.135. So the answer is 0.135. So I will again repeat once. So it is said uh, there is a machine X and there is a machine Y. It is executing the same program P and P. X has a CPI of 2.5. The clock cycle is unknown. Suppose the instruction count is X, small x. For machine Y, same program P, CPI is 1.5. And the clock cycle is 1 by 4 gigahertz. So 1.4 gigahertz is basically 1 by 1 by 4. So the clock cycle will be, if you solve this equation, since the execution time of both the program P in X and Y are same, so this will be the equation. The execution time of this execution time in X or execution time in Y. So we will find the clock cycle will be 1.35, 0.135. So what will be the clock frequency? So frequency X will be 1 by 0.135. That will come down to 740. So this is NS GHZ. So any doubts? Okay. So if the program is request, can we equate it? Yeah, we can equate it. Like there is so it is here given that program is same. Uh, like suppose if the question is there are two different programs but the execution is same, execution time is 10, then we can, why not we can equate it? It's just basic maths. Here the condition given is that program is same. Okay, so I will go to the next problem then. So the question is, suppose we have a CISC instruction set architecture implementation. There are four instructions: load, store, ALU, and branch, and all have a relative with a relative frequency 25%, 25%, 40%, and 10%. Exactly. The CPI are 3, 2.5, 1, and 6. So what is the overall CPI? So it is said we have a CISC ISA, and it have the following instructions. So load 25% of the instruction, and it has a CPI of 3. Store has 25% of the instruction, and it has a CPI 2.5. ALU 40% of the instruction, and it has a CPI of 1. Then is branch 10% of the instruction, and its CPI is 6. So what will be the overall CPI? So overall CPI will be, so what we will do, we will add with respect to its frequency, weighted add, you can say. So it will be 0.25 into 3 plus 0.25 into 2.5 plus 0.4 into 1 plus 0.1 into 6. So if we add it up, it will be 0.75 plus 25.25 into so 0.25 into 2.5, it will be 0.625 plus 0.4 plus 0.6. So it will come down to 1.7, 5, 2.375. So overall CPI will be 2.375. So I will again repeat. So we have a CISC instruction set architecture. There are four instruction types: load, store, ALU, and branch. So we have just tabulated the question. So it has a frequency of 25%, 25%, 40, and 10% respectively. they have a CPI of 3, 2.5, 1 and 6. So how to calculate the total CPI? CPI is, we will just additive, what is called additive sum. So the frequency and the corresponding CPI. So basically 0.25 into 3 plus 0.25 into 2.5 the CPI, then zero point 0.4 the frequency, then again the CPI, then again 0.1 into 6. So we will add this up, so it will come down to 2.375. So that will be the overall CPI. So any doubt you can ask. So if you have no doubt, then I will go to the next question. So, so consider a program with 50 million instructions. So it has 50 million instructions. So a machine requires 25 milliseconds to execute this program. So what will be the MIPS rating of the machine? So what is MIPS? MIPS is million instruction per second. So it generally comes from the so here it is given. So here it is given the what is that? The program has the IC count is 50 million, instruction count is 50 million, and the XT is and the XT is 25 milliseconds. So what will be the what will be the MIPS? So MIPS is given by the formula IC divided by XT into 10 to the power minus 6. So here IC given is 50 million and XT given is 25 milliseconds. So it will be 50. So this will be 50 into 10 to the power 6. This will be 25 into 10 to the power minus 3. So it will be 15 to 10 to the power 6. 15 to 10 to the power 6 divided by 25 into 10 to the power minus 3 into 10 to the power minus 6. So that will give the MIPS value as 2000. So this will be the answer. So I will repeat again. So the question is, what will be the MIPS rating of the machine? So given number of instruction is 50 million and the execution time is 25 milliseconds. So MIPS is given by the formula IC by xt into 10 to the power minus 6. So the execution time is given, IC is given, we will substitute the values and the value that will come out to be is 2000. So you have any doubt regarding this? Okay, I will move to the next question then. So given program execution time is made up of 75% CPU time and 25% IO time. So which is a better enhancement? That is one, increasing the CPU speed by 50% or reducing the IO time by 50%, by half. The reducing the IO time by half, not 50%. So we will be using the Amdahl's law. So what does Amdahl's law state? So it gives that speed up is equals to 1 by 1 minus f plus f divided by s. So f is the fraction of enhancement and s is the corresponding enhancement, or you can also call it as speed up of that part, right? So here two schemes are given. So scheme 1 says and scheme B. So here scheme 1 is increasing the CPU speed by 50%. So the program has 75% CPU and 25% IO time. So first part says the increasing the CPU time by 50%. So what will be the speed up? One by what is the fraction that is not used? So this is the for the CPU. So CPU IO. So speed up will be one minus f by s. So here it will be 1 minus 0.75 because that is the fraction of CPU time plus 0.75 divided by 1.5 because the speed is increased by 50%. So 50%, so it will be so this, if you solve this, the speed up will come out to be 1.33. Now for the IO part, speed up will be using the same formula, 1 minus 0.25 plus 0.25 0.25 divided by 2, because the IO time is halved. So if you solve this, it will come out to be 1.14. So which policy gives the better enhancement scheme? So which is a better enhancement? That is the increasing the CPU speed by 50%, because see the value is 1.33, and for reducing the IO time by half, the value is 1.14. So in this case, the better enhancement is like increasing the CPU speed. So this is a what I will say is, this is a basic this is a basic application of Amdahl's law. So the this is how this theory is being applied to um, various operations like this. So I will repeat again. So the Amdahl's law. The question is, the program execution time is made up of 75% CPU time and 25% IO time. So which of the following is better enhancement? So it has to be solved using the Amdahl's law, because it states that a fraction of enhancement and the speed up is basically 1 by 1 minus f, that is a non fraction that is not enhanced, by the plus the fraction that is enhanced, and the corresponding speed of s. So if you substitute the values corresponding to this that is given in the question, so this will be the final result, 1.13 and 1.14. Any doubt? So I will go to the next question then. So given a program, so let a program have a portion FE of its code enhanced by 4 times to run 4 times faster. Enhance its code enhanced to run 4 times faster, and and the corresponding yield for the system speed up is 3.3 times faster. So what is the fraction enhanced? So suppose so we have a code, a portion of a code that is, suppose, a part if. So it has been enhanced to run 4 times faster, and the corresponding speed up for the system is 3.3. So what is the fraction of the code that has been enhanced? We need to find out. Again, we will apply the same Amdahl's law. Which gives speed up equals to 1 by 1 minus f plus f by s. So in this case, what will be? So it will be the overall system speed up is 3.3, right? It is given. And we have to find the fraction of the code that has been enhanced. Let it be f. And the code has been faster. So this is the system fast. Sorry. So this is the part of the system speed up, and the part of the program speed up is 4. So we need to find the value of f. So we can write this as 1 minus 3f by 4 equals to 1 by 3.3, or f equals to 1 minus 3.3 into 4 by 3. So if we solve this, it will come out to be 0.929. So this is another application of Amrit's law, where we are finding out the part of the like what is the fraction that has to be enhanced. So one more thing you will notice that. So what can be the maximum speed up that is possible? So maximum speed up that is possible is that when this one tends to infinity. So in that case, that this is this is the part. So max speed up will be 1 by 1 minus f. So in this case, the maximum speed of what it can be 1 minus 0.929. So that will be that will be 14.08. So that can be the maximum speed up. Any doubt? So any doubt from the previous questions, I can show it again. Yeah, max speed up is like suppose so speed up is basically 1 minus 1 minus f f divided by s. So this is the fraction of the system that is being enhanced, and this is the enhancement. Suppose I'm able to enhance it to infinity, right? So this part will tend to 0. So that means like that means that this part of the question program, it takes it for execution, it just is negligible, the execution of that part. So that case the maximum speed up that is possible is 1 by 1 minus f. So in our case, if we substitute the values, that is in previous question we received the value as 0.929. So if f is equal to 0.929, so maximum speed up will be 1 minus 0.929, and the value is 14.08. So again, like if we take this question, like the program execution time is made up of 75% CPU and 25. So suppose for the CPU, the CPU speed increases by 50%. In case of 50%, it becomes like CPU operation does not take a minute scale time, like it cannot be calculated. So that in that case, this portion will become 0 because s will be infinity. So in that case, the speed up will be only this much part. So it will be 1 minus 1 by 0.25. So that will be 4. So that is the maximum speed up that will be possible in that case. So any other question you need? I will repeat if you ask. Many have joined late. You can ask which question to repeat. Okay. So if you check this question, so the question given is that a program requires 1000 instructions to execute. The CPI given is the number of cycles per instruction is 1.5, and and uh, and the clock frequency is 2 gigahertz. So time required to execute the program. So the time you see execution time is given by this formula. IC equals to CPI or uh, that CPI into C. So IC given is 1000, CPI is given is 1.5, frequency is 2 gigahertz. So C equals to 1 by F. So 1 divided by 2 into 10 to the power 9. So in that case, you substitute the values IC, CPI. C is basically 1.1 divided by F. So if you calculate this, so it will come down to 750 nanoseconds. Okay, so question 3 and 4. Okay, I will repeat question 3 and 4. So the question is, what is the speed up that can be achieved? So you have a program whose instruction count is 1000. Instruction count is 1500. CPI is 2. Clock cycle is 1 nanosecond. Suppose we have a new compiler for the same program, and the new for that compiler, it's the instruction count is 2500, CPI is 1.5, and it is running faster with a clock cycle 0.5 nanoseconds. So what is speed up? Speed up is basically given by this formula. Speed up 1 to 2 to 1 is basically performance of 2 divided by performance of 1. So how is performance calculated? Performance is calculated as 1 by execution time. So that will be 1 by divided by x2 xt2 divided by xt1. So again, like previous question, we substitute the values from the problem to calculate the xt1 and xt2. Now using this, we just calculate, the value will come out to be 1.6. This one is clear. Okay, so the question number 4. So question number 4 says we have a program that is P. It is being executed on two different machines, that is X and Y. So what is the CPI in the first one? It is 2.5. CPI in the second one, that is Y, 1.5. Clock frequency of the second is not given, of the first it is given, so of the second is given, first is not given. So it is given as 1.5 for the second, at 6 gigahertz is given. So this is 1 by 4 6 gigahertz, that will be the clock cycle. IC, it says that in the first machine, the IC count, let it be X, and for the second machine, then it will be 10%. It executes the program in 10% less instruction. It's 10% less instruction, so it will be 0.9x, x minus 10% of x, that is 0.9x. Now it is given the execution time of P in both x and y is same. Both x and y is same. So then we will write the execution time formula for x, that is machine x, and also for machine y. So 25 into c into x equals to 1.5 divided by 1.4 into 0.9x. So if from this we will find the value of c, that is 0.135. Now to find the frequency, so like we know, clock cycle is equals to 1 by frequency, or frequency equals to 1 by clock cycle. So frequency will be 1 divided by 0.135. So that will come down to 0.740 gigahertz. This is clear. Any more doubts? If you have any doubts, you can ask. Okay, so we will again meet on the next week, same time, 6 Tuesday 6 p.m. Thank you.